Okay, let's get started. Hello, I'm Yuta, and I go by Kohi online. I'm really happy to be back here at Tri-City Tokyo as a speaker again. 10 years ago, I spoke at the very first Tri-Swift conference. At that time, Swift was still on version 2. I talked about throws and try, which had just been introduced, and discussed what syntax Swift should use for async await if it were to adapt the feature. This code is taken from the slides of that talk. I explained that based on the relationships among throws, result, promise, and async, to stay consistent with throws and try in Swift, Swift's async await should play a different role from async await in JavaScript and TypeScript. Now, 10 years later, Swift uses the same async await syntax that I talked about back then. I didn't participate in the discussion about Swift concurrency on Swift forums, so this was just a coincidence. Still, I'm very happy that something I imagined at that time actually became real. Today, I want to talk about throws, try, and async await again, and about AI. Right now, the situation surrounding us as software developers is changing dramatically with the rise of AI agents. I started using Cloud Code as soon as its research preview was released in February last year. I quickly realized that AI agents were far better at coding than AI chatbots, even though they were using the same models. When using an AI chatbot for coding, first, I explain to the AI what I want to implement. The AI writes code. I copy and paste that code into my IDE. The IDE reports type errors. I fix them myself or send the errors back to the AI. Because AI frequently generated code with type errors, I assumed that this was the limit of their coding ability. Cloud Code also produced type errors, but the crucial difference was that it could correct them on its own. It built the code, checked the errors, and fixed them. We also rely on the IDE and compiler when we write code. We don't get everything right from the beginning. The same is true for AI. If it gets the right feedback about its mistakes, it can correct them. Even when I was coding with an AI chatbot, I did the same thing. I sent compiler error messages back to the AI and asked it to fix them. But seeing Cloud Code solve problems autonomously gave me a completely different impression. It made AI seem much smarter. In this way, giving AI agents an appropriate means of verification is extremely important. The Cloud Code best practices say this. Give Cloud a way to verify its work. Cloud performs dramatically better when it can verify its own work. And Boris Chany, the inventor of Cloud Code, also says this. A final tip, probably the most important thing to get great results out of Cloud Code. Give Cloud a way to verify its work. If Cloud has that feedback loop, it will improve 2 to 3 times the quality of the final result. Compiler feedback is the most basic form of verification available to an AI agent. By getting feedback from the compiler, an AI agent can eventually produce code without compilation errors. If we think of the build process as a means of verification, then it matters what kind of syntax and type system a programming language has, because that determines what kind of feedback the compiler can provide. In that sense, Swift is a very interesting language. In Swift, throws is part of a function's type. It indicates whether a function may throw an error. But in many widely used statically typed languages today, such as TypeScript, C#, Kotlin, and Dart, whether a function may throw isn't part of the function's type in a way the compiler checks. So even if you look at the function declaration alone, you can't tell whether that function may throw. You might be wondering about Java. Java's checked exceptions are a great feature, but Java also has some difficulties. One difficulty is that designing exception types can be difficult because Java doesn't have a direct equivalent of Swift's untyped throws, and you can still catch the exception class, but because runtime exception is a subclass of exception, doing so can easily mix recoverable errors and logic failures. So, okay, so now let's go back to TypeScript. When I write TypeScript, I often feel uneasy about whether errors are being handled correctly in the code. For example, if you look at code like this, can you confidently say which line may throw an error? Take this find user function, for example. Could it throw an error? Maybe it simply looks up the user in a collection and returns it. In that case, it probably wouldn't throw. But maybe it accesses a database and fetches the result. In that case, it might throw a database connection error. You might be able to tell whether it can throw by checking the documentation. But comprehensive documentation is rare. Even if the documentation exists, whether we can trust it is another question. The compiler doesn't check what the documentation says. We don't know whether it is maintained correctly, and in the end, if we want to be sure, we have to read the code. In Swift, this is simple. We can tell just by checking whether the function declaration includes throws. Of course, even without a language feature like throws in Swift, it's still possible to express the possibility of errors statically by using something like a result library. But in that case, you end up with fragmentation, with different frameworks adapting different styles. Swift once had a similar problem. Before async await, asynchronous code was written in many different ways, such as with callbacks, future, and third-party libraries. But those styles didn't combine naturally with throws. As a result, error handling styles were fragmented as well. Swift 5.5 improved this situation significantly by introducing async await. Today, when asynchronous code can fail, expressing it as async throws is the standard approach. Now, I wanted to quantify how having throws as part of functions type affects AI agents. First, I built a tool that generates equivalent functions in Swift and TypeScript. This tool takes parameters such as a function name, call depth, and branching factor, and generates a function and a tree of functions it calls, all filled with generated meaningless code. For both Swift and TypeScript, it outputs two variants, one that may throw errors and one that doesn't. For the actual experiment, I set the call depth to 4, the branching factor to 3, and generated 18 meaningless steps in each function. Using this tool, I created two functions, find user and find group. Find user looks up a user by name, and find group looks up the group that the user belongs to using user ID. The tool generates two variants of functions, throwing and non-throwing. In TypeScript, the signature is the same in both throwing and non-throwing variants, because function declarations don't include throws. Using these functions, I asked the AI agent to implement the function list belonging groups. This is the prompt I gave to the AI. Implement a function list belonging groups. This function should satisfy the following specification. 1. For each user name in the given array, retrieves the user using find user. 2. If the user is found, retrieves the group that the user belongs to using find group. 3. If a user or a group is not found, skip that element and continue processing the rest. 4. Remove duplicates from the resulting groups using their ID. 5. Print each group's name to standard output 1 per line. 6. Apply appropriate error handling, in particular log errors so it is clear where they occurred. However, do not add unnecessary catch handling at call site where errors are not thrown. For TypeScript, I used the same prompt with slight changes to reflect the syntactic differences. I examined whether the generated implementation of list belonging groups handled errors correctly, and how many tokens were consumed during the implementation. I ran the experiment 20 times in total, 5 runs each for Swift and TypeScript in both throwing and non-throwing cases. The results looked like this. In Swift, errors were always handled correctly. In TypeScript, on the other hand, errors were often not handled appropriately. This is the actual code that the AI generated. From this, we can infer that the AI only looked superficially at find user and find group in TypeScript and made incorrect judgments about whether error handling was necessary. Actually, I checked the logs from several sessions, and I found that the AI only read the files where find user and find group were declared. Next, the input token counts looked like this. There was no major difference in input token usage because in both Swift and TypeScript, the AI only looked at shallow parts of the code chain. To make TypeScript handle errors appropriately as well, I tried adding this one sentence to the prompt. If you conclude that errors are not thrown, read the code all the way to the libs and make sure that the relevant path truly does not throw. Let's call this the strict prompt. I ran the experiment again using the strict prompt, and the results looked like this. By prompting the AI to check the code all the way to the libs, it was able to handle errors appropriately in TypeScript more often. However, the input token count increased significantly in TypeScript. This reflects the fact that in TypeScript, you cannot tell whether an error may be thrown unless you trace the code all the way to the libs. If we compare the results of the two prompts, they look like this. It is clear that with the strict prompt, input token usage increases significantly in TypeScript. Swift also shows some increase in token usage, but that seems to be because this instruction to read the code all the way to the libs sometimes makes the AI look beyond just the throws in the function declaration. The results of these experiments suggest that having throws as part of a functions type in Swift helps guide AI agents towards appropriate error handling with fewer tokens. Note that this experiment was designed to focus on just one aspect of programming languages, whether throws is part of a functions type. Other factors were excluded as much as possible. So these results alone don't mean that Swift is more suitable for agentic coding than TypeScript. Up to this point, I have focused on throws as one aspect of Swift's type system. But modern Swift has another very interesting feature. That is, it uses the type system to prevent data races. At first glance, it may seem very difficult for compiler to guarantee that data races never happen. But Swift achieves this by generally preventing non-sendable values from crossing boundaries between concurrency domains. At present, AI agents often don't handle this very well. We sometimes see them respond to isolation-related errors by blindly adding at main actor everywhere. But I think that's because language with mechanisms like isolation are still there today, so AI hasn't learned to handle them well enough yet. Or perhaps the problem is simply too difficult for current AI capabilities. But fundamentally, this kind of isolation mechanism should help AI agents as well. In the future, it may help them in a similar way to throws. Finally, I'd like to step slightly outside the main topic and introduce some other forms of verification that can be useful in iOS app development beyond compiler feedback. First, testing. In addition to compiler checks, we can actually run the code and verify its behavior through tests. The importance of testing has been emphasized for a long time. But I think it has become even more important when working with AI agents. Interestingly, software engineering knowledge about how to design code that is easy to test becomes even more useful in the age of AI. We can even make AI agents check UI layout. Since Xcode 26.3, Xcode has provided an MCP server, which allows AI agents to access Xcode. One useful feature is access to previews. With that, an AI agent can inspect a rendered view and check whether the layout looks right. It's also possible to have AI agents verify the behavior of an app running in the simulator. Unfortunately, the current Xcode MCP server doesn't support that capability yet. But with a third-party tool such as Xcode Build MCP, an AI agent can operate an iOS app in the simulator on its own. Verification can also be useful outside coding. I'm currently working on a personal project, a trading card game where players can create their own cards using foundation models and image playground. I generated images for the preset cards using image creator in image playground. But image creator isn't very reliable yet, so it isn't easy to get exactly the images I have in mind. To address that, I created a CLI tool for working with image creator and tried handling the image generation process over to Cloud Code. In this workflow, for each monster, I first describe its appearance in text. Based on that, Cloud Code comes up with a prompt, checks the generated image, and verifies whether it matches the described appearance. If Cloud Code judges that the result isn't good enough, it modifies the prompt and tries again. This made it possible to automate the process of generating those images. In this way, the performance of AI agents depends greatly on how we use them. Some people say agentic coding is incredibly useful, while others think it only leads to broken code bases. But in reality, that depends on many factors: the model and the tools we use, the size of the code base, the kind of problem we work on, and as this talk has tried to show, how effectively we give AI agents ways to verify their work. If we judge too soon that AI agents are not useful, we may misjudge the situation. To understand how useful AI is, we need to keep learning and working through trial and error. AI will continue to evolve, and what we can do with AI will keep growing. We can no longer ignore AI in software development. So let's enjoy coding with AI in this wonderful language, Swift. Thank you for listening.